classical theory and its demerits, and then the assumptions of quantum theory, Planck's radiation law. Then we have discussed de Broglie's concept of matter waves, the properties of matter waves also we have discussed, dual nature of matter. Then the significance of wave functions associated with the material particle and its properties also we have discussed. Psi, the instantaneous state of a particle can be described by a wave function psi of xyzt, where xyz are position coordinates, t is the time coordinate, and this wave function is a single valued, finite and continuous. And actually it is having no physical significance. It has a complex nature of the type x plus iy, but the probable density is having physical significance. If psi is x plus iy, so complex quantity is x minus iy. The product of these two, psi star, which is mod psi square, is x square plus y square, which is real in nature, and it has significance. And psi is said to be normalized function. If the probability of finding a particle over a volume is equals to 1, then the wave function is called as a normalized function, and the psi is also a normalized function. Then Schrodinger, he has developed some mathematical reformations in the same equation. We can represent both the wave nature as well as particle nature. So for that, it can be simplified for one dimension. A particle of mass and moving with some velocity, the wave function associated with the particle is represented by xt. Then using Planck's equation, de Broglie's theory of matter waves, and using the law of conservation of energy, finally you can obtain Schrodinger time dependent equation. Then Schrodinger time independent equation also we have derived. These two we have derived. And one application is there which is particle in one dimension box or infinite square wave potential. So that derivation, you ready with your books, and you should note down those derivation parts also. You take the heading. Is this visible? Presentation? Students?
Yes,
Girls?
sir.
Yeah. Take the heading. Particle in one-dimensional potential box. This is an application of the Schrodinger time independent wave equation. Take the heading. Particle in one-dimensional box. Take the heading. Particle in a one-dimensional potential box. And you take the diagram also. At the bottom, some small diagram is given. Shall I start, students? Boys, did you finish this figure? Girls,
Yes, sir.
okay, listen this carefully. So, particle in one-dimensional potential box is also known as infinite square wave potential. It is an application of Schrodinger time independent wave equation. So, we are using Schrodinger time independent wave equation. Why you should take this problem? Because by taking this, by applying Schrodinger time independent wave equation, we can verify the quantum nature of the particle. So the particle like electron or proton or small tiny particles, they have some discrete nature. According to quantum theory, only certain discrete energy levels are possible. The energy distribution is not continuous according to quantum theory. So by taking this application, this problem, using Schrodinger time independent wave equation, we can write for the expression for the wave function associated with the particle in one dimensional box, and also the energy expression, and from the energy expression we can show that the particle possessing discrete energy structure or the energy distribution is not continuous and it follows certain quantum rules. So this we are going to verify by taking this problem. So to understand this, let us consider a particle like electron of mass in one-dimensional potential box of width L. So consider a one-dimensional box of length L suppose, and in that let us consider a particle is zero. The particle is present. Inside the box, the particle is free to move and it is treated as a free particle and possesses a constant potential. And conveniently, we can assume that the potential V is equal to 0 inside the box. And at the boundaries, so there are the length of the box is L according to the assumption. So the boundaries are 0 and L, and at the boundaries and below and above these boundaries, above the box, the particle has infinite potential. So the potential is very high. We will consider it as an infinite potential. So this is the description of the particle in one-dimensional box. And psi is the wave function associated with the particle. According to de Broglie, any particle like electron, whether it is charged or uncharged particle, can be associated with a wave, and psi is the wave function associated with the particle. So here also we are assuming that psi is the wave function associated with the particle. Once again, I will repeat this. This is a straight application of Schrodinger wave equation. So this is a particle in one-dimensional potential box, how it behaves, and what is the expression for the wave function, and what is the energy expression we are going to discuss. And from the energy expression, we can observe the quantum nature of the particle, how the energy of the particle will be distributed in the one-dimensional box of certain definite length. To understand this, let us consider a particle like electron is present in a one-dimensional box of length L. So inside the box, the particle is free to move and it is called as a free particle and it possesses constant potential, and conveniently the potential V can be taken as zero. And at the boundaries and below zero and above L, the particle has very high potential and conveniently it can be treated as infinity. And psi is the wave function associated with the particle. Inside the box, the particle, the psi is having physical significance because the probability of finding the particle inside the box is 1 always, and the probability of finding the particle at the boundaries and outside the box is 0. So inside the box only psi has significance. At the boundaries and below 0 and above L, the particle has no physical significance. So this is the description, and you can write boundary conditions. Potential Vx is equal to 0 for 0 less than or equal to x, or less than or equal to L. That means inside the box the potential is 0, and at the boundaries and outside the box the potential is infinite. Also, the probability of finding the particle inside the box is 1. That means always the particle will be in the box only, it won't cross the boundaries. So only within the box only the wave function has significance, and at the boundaries psi is equal to 0, and below 0 and above L, psi is equal to 0. So psi is equal to 0 at x is equal to 0 and at x is equal to L. So these are the boundary conditions for the particle. Please note of this. Here you write here are 4 points. I'll explain. This is an application of, this means particle in one-dimensional potential box. This is an application of Schrodinger time independent wave equation. This is an application of Schrodinger time independent wave equation. This is an application of Schrodinger time independent wave equation. Let us consider a particle of mass m. Let us consider a particle of mass in one-dimensional potential box of length capital L. Let us consider a particle of mass m in one-dimensional potential box of length L. Inside the box, the particle is free. The particle is a free particle. Better you write. The particle is a free particle and possesses constant potential. These points are not given in PPT, that's why I am explaining. And possesses constant potential. Hence, inside the box, the potential V, can be conveniently taken as zero. At the boundaries, next point, at the boundaries and outside the box, the particle has very high potential. And can be taken as infinity. Next, let psi is the wave function associated with the particle inside the box. Let psi is the wave function associated with the particle inside the box. Let psi is the wave function associated with the particle inside the box. The probability of finding the particle inside the box, is always 1 and outside the box is 0. Therefore, psi has significance only inside the box. Psi has significance only when the particle is inside the box. Only when the particle is inside the box. Next, the boundary conditions are, now you write these two, which are there in the PPT. Vx is equal to 0 for 0 less than or equal to x less than or equal to L, and Vx is infinity otherwise. That is, x means it's the position of the particle. At the boundaries and outside the box, the potential is infinity. That is the meaning of otherwise. And second one is psi is equal to 0, at x is equal to 0 and x is equal to L. Only inside the box, psi has significance. At the boundaries and outside the box, the psi is 0. These are the boundary conditions. Is this clear, boys? Please respond from boys' side. Yes?
Yes, sir.
Girls?
Yes,
Somebody
sir.
respond. Okay. So these are the boundary conditions. Now we should apply Schrodinger time independent wave equation. So from Schrodinger time independent wave equation, you write d square, dou square, better you write Rho square psi by dou x square plus 2m by h cross square into e minus v into psi is equal to 0 is Schrodinger time independent wave equation. From Schrodinger time independent equation, we have dou square psi by dou x square plus 2m by h cross square into e minus v into psi is equal to 0. But from the boundary condition, inside the box, the potential V is equal to 0. Therefore, it becomes, you put V is equal to 0, d square psi by dou x square plus 2m by h cross square e into psi is equal to 0. And let us assume k square is equal to 2m e by h cross square. Then we can get dou square psi by dou x square plus k square psi is equal to 0. We will be getting a second order differential equation. So the solution for above type of second order differential equation is psi of x is equal to a sin kx plus b cos kx, where a and b are unknown constants. We should evaluate these constants. So for any second order differential equation of that type, dou square psi by dou x square plus k square psi is equal to 0, the probable solution is psi of x is equal to a sin kx plus b cos kx, where a b are unknown constants. So we have taken Schrodinger time independent wave equation. Yesterday we have derived this. Dou square psi by dou x square plus 2m by h cross square into e minus v into psi is equal to 0. But inside the box, the potential is 0. You keep v as 0. Then we will be getting dou square psi by dou x square plus 2m v by h cross square into psi is equal to 0. Let us assume k square is 2m v by h cross square. Then you can obtain dou square psi by dou x square plus k square psi is equal to 0, which is a second order differential equation. The probable solution is given by psi of x is equal to k sin kx plus b cos kx, equation 1. Please note that. Should I proceed? Friends?
Yes, sir.
So for the calculation of this A and B, you should apply boundary conditions. So we have already discussed when x is equal to 0, psi is equal to 0. And also when x is equal to L, then also psi is equal to 0. At the boundaries and outside the box, the wave function has no significance, or it can be treated as 0. So first at x is equal to 0, we have psi is equal to 0. Therefore, instead of x, you should substitute in the previous expression, which is a sin kx plus b cos kx. Our equation is psi is equal to a sin kx plus b cos kx. So a sin k of 0 plus b cos k of 0 instead of x, you should substitute 0 is equal to 0 because psi is equal to 0. So from this you can get sin 0 is 0. So cos 0 is 1. From that you will be getting b is equal to 0. So substituting b in equation 1, we can get psi of x is equal to a sin kx. Because b cos kx is there, but b is equal to 0, the entire term will become 0. So the general solution is psi of x is equal to a sin kx. Please note down this. Similarly, we have at x is equal to L, psi is equal to L. So applying the second boundary condition, at x is equal to L, psi is equal to 0. Again, we will be getting 0 is equal to a sin kl. Instead of x, you should substitute L. So a sin kl plus 0 cos kl, because b is equal to 0. Therefore, a sin kl is equal to 0. But a should not be equal to 0 because already b is equal to 0. So a sin kl is equal to 0 and a is not equal to 0. Therefore, sin kl is equal to 0. or KL is equal to n pi or K is equal to n pi by I. So finally, the equation will become, actually we have psi of x is equal to a sin kx, but k is equal to n pi by L. Therefore, the wave function associated with the particle inside the box is psi of x is equal to a sin n pi x by L. Is it okay, students? Understood?
Yes, sir. Sir, one show the previous slide.
Yeah. Actually, you have equation 1 psi of x is equal to a sin kx plus b cos kx. Now you have boundary condition. Psi is equal to 0, then x is equal to 0. Also psi is equal to 0, then x is equal to L. We are going to apply both. So first we should apply when x is equal to 0. So if x is equal to 0, then psi is equal to 0. Therefore 0 is equal to a sin k0 plus b cos k0. So sin 0 is 0 and cos 0 is 1. From this you will be getting b is equal to 0. Therefore, second boundary condition is if x is equal to L, psi is equal to 0. So again, 0 is equal to a sin kl plus b cos kl, but b is 0. So a sin kl is equal to 0. Here there are two possibilities. Either a is 0 or sin kl is 0, but a is not equal to 0, because if a is also 0, then wave function does not exist, because both a and b will become 0. So a is not equal to 0, and thus sin kl is equal to 0, or kl is equal to n pi, or k is equal to n pi by L. Hence, the equation becomes psi of x is equal to a sin n pi x by L. This is the wave function associated with the particle in the one-dimensional box of length L. Now you should evaluate the constant A. Clear? Students, boys, shall I proceed?
Yes, sir.
So we have discussed the earlier, the probability of finding the particle inside the box is 1 always. The particle will not cross the box, and at the boundaries and outside the box, the probability of finding the particle is 0. So inside the box, psi is the wave function associated with the particle, which is a normalized wave function. And yesterday we have discussed the properties of a wave function. The psi is said to be normalized if the probability of finding a particle over a volume is equals to 1. The same we are applying here, because the probability of finding the particle inside the box is equals to 1. Psi can be called as a normalized function. So the condition for normalized function is integration 0 to L, because the length of the box, lower limit is 0, upper limit is L. So between these limits only the particle will be existing inside the box. So integration 0 to L mod psi x whole square into dx is equal to 1. Because it is one dimension we have considered. Actually it should be dv, but we have restricted to one dimension. So the normalized condition for psi is integration 0 to L mod psi x whole square dx is equal to 1. Because this should be equal to 1, then only psi is called as normalized function. And psi x is a sin n pi x by L. So by substituting that value, integration 0 to L, a square sin square n pi x by L dx is equal to 1. And a square can be taken out, integration 0 to L. So sin square theta is written as 1 minus cos 2 theta. The same we did here with simple mathematics. So it is a square 0 to L half into 1 minus cos 2n pi x by L dx, that is equal to 1. Again you can bring 2 as common, and by putting lower limit and upper limit, finally we will be getting a square by 2 into L is equal to 1, or A is equal to under root 2 by L. This mathematics part, I think you understood. Otherwise in the physics you know you need not do. by taking a square into 0 to L half 1 minus cos square n pi x by dx is equal to 1. By simplifying, we get finally a is equal to under root 2 by L, because we don't focus on the derivation part in physics. The final expression is important. You can write straight away, but you should remember it this one. A is equal to under root 2 by L. Please copy these steps. Shall I proceed, students? Girls?
Sir, give us a minute.
Okay. Shall I proceed?
Yes, sir.
So the final expression becomes A can be written as under root 2 by L. Therefore, psi n is equal to, actually psi n is A sin x sin n pi x by L. A is under root 2 by L. Therefore, psi n is equal to under root 2 by L sin n pi x by L. So this is the expression for the wave function associated with the particle. And also, we have assumed that k square is 2m by h cross square, or E is equal to k square h cross square by 2m, but k is 2m n pi by L. So energy can be written as E is equal to, instead of k square, you can put n pi by L whole square. H cross square can be written as h by 2 pi whole square by 2m. So finally, we'll be getting E is equal to n square h square by 8m L square. This is the expression for the energy of the particle in one dimension box of length L. For particles like electron, this wave function psi n and the corresponding energy En are called eigenfunctions and eigenvalues of the quantum particle. So psi n is called as eigenfunction and En is called as eigenvalue. Please note down this. Psi n is equal to under root 2 by L sin n pi x by L is equation 3, which is the eigenfunction or expression for the wave function of a particle in one dimension box. And E is equal to En is equal to n square h square by 8m n square is the expression for the energy of the particle. Psi n is called as eigenfunction and En is called as eigenvalue. This is the expression for energy of a particle in one dimension box of length L. Did you copy, students?
Yes, sir.
Now, so you should draw this energy diagram also. So if n is equal to 1, E1 is equal to h square by 8ml square. If n is equal to 2, it is 4h square by 8ml square, which is 4E1. And if n is equal to 3, then it is 9E1. That means the first possible energy is E1 and the second one is 4E1. So 2E1, 3E1 are not permitted. And the second next energy level is 9E1. 5, 6, 7, 8 are not possible. So it straight away explains the quantum nature of the particle. All energy levels are not possible. Only certain discrete energy levels are possible for the particle to have its energy. So this indicates the particle is a quantum particle. Energy is quantized. That can be verified by taking this Schrodinger time-independent equation for a problem of a particle present in one-dimensional box of limited length. And this is the expression for wave function. So first for psi1, it is real. For psi2, it is, has a complex nature. It has both real and complex nature. And psi3 also it has both real and complex nature because it has a positive cycle as well as negative cycle. But the probable density mod psi1 square is or mod psi2 square mod psi3 square, this negative component, negative cycle is vanishing. X plus I y into x minus I y, x square plus I square only, y square only. The probable density has physical significance is represented here. So the energy also, what I have explained previously, energy is E1, 4E1, 9E1, 16E1, 23E1 like that. The energy will be changing discontinuously, showing the quantum nature of the particle. So this is the graphical representation of the wave function as well as the energy of the particle in one dimensional box. You should draw this diagram also in the exam. So in brief, once again just I'll brief this one. So this is an application of Schrodinger time independent wave equation. Here we are going to describe the wave function of a particle using Schrodinger time independent wave equation and its quantum nature. Further, consider a particle of mass m in one-dimensional box of length L. Inside the box, the particle is a free particle and possesses constant potential. So conveniently, the potential is taken as zero. And at the boundaries and outside the box, the particle has very high potential and it can be considered as infinity. So the probability of finding the particle inside the box is 1 and psi is the wave function associated with the particle. So psi has significance only when the particle is inside the box. At the boundaries and outside the box, the wave function has no significance. In that sense, we can write the potential boundaries boundary conditions. Potential V is 0 for 0 less than or equal to x less than or equal to x, and potential is infinity otherwise. That means at the boundaries and outside the box. Also, psi is equal to 0, at x is equal to 0, and at x is equal to L. So, from Schrodinger time independent wave equation, we have dou square psi by dou x square plus 2m by h cross square into E into psi is equal to 0. But V is equal to 0 inside the box. So, you will be getting dou square psi by dou x square plus 2m by h cross square into psi is equal to 0. Let us assume k square is 2m by h cross square. Then it becomes dou square psi by dou x square plus k square psi is equal to 0. Now, the solution for the above equation is psi of x is a sin kx plus b cos kx, where a, b are unknown constants. Now, you should apply boundary conditions to evaluate a and b. When x is equal to 0, psi is equal to 0. Therefore, a sin k0 plus b cos k0 is equal to 0. So, sin 0 is 0. So, here from the equation b will become 0. Therefore, the equation is psi of x is equal to a sin kx. And second boundary condition is at x is equal to L, psi is 0. Therefore, 0 is A sin Kl plus 0 into cos Kl because B is equal to 0. Therefore, A sin Kl is 0. Here, there are two possibilities. Either A is 0 or sin Kl is 0. But A cannot be equal to 0 because already B is equal to 0. So, equation will not exist. Solution will not exist if both A and B become 0. So, sin K must and should be equal to 0. From that, we get K is equal to n pi by L. Therefore, the wave function associated with the particle in one dimension box is A sin n by x by L. To evaluate A, you should apply normalized condition. The probability of finding the particle inside the box is 1. Therefore, the wave function is called as normalized wave function. The condition for normalized wave function is integration 0 to L mod psi x square dx is equal to 1. If this is equal to 1, then only it is called as a normalized function. So instead of psi x, you can substitute a sin x, a sin n by x by L, and by simplifying this, using properties of this integration, and by using limits, finally you can get a is equal to under root 2 by L. Therefore, the wave function can be written as under root 2 by L sin n by x by L. Also, we have k square is equal to 2m by h cross square, or E is equal to, you bring h cross square there, it becomes k square h cross square by 2m. But k square is n pi by L. So it becomes n pi by L whole square, and h cross is h by 2 pi whole square by 2. From this, you can write E is equal to n square h square by 8m h square. So the wave function psi n is called as eigenfunction, and the corresponding energy En is called as eigenvalue. And if you write the representation graphically for different values of n, for n is equal to 1, we have E1 is equal to h square by 8ml square. For n is equal to 2, it is 4E1. For n is equal to 3, it is 9E1. It straight away explains the discrete fields of the particle, because 2E1, 3E1 are not permitted for the particle to occupy, and also 5, 6, 7, 8 energy levels are not permitted. It indicates the quantum nature of the particle. So this is the graphical representation of wave function psi and mod psi square and the energy level diagram of a particle in one dimension. So this we have discussed in this chapter. In the chapter, at the beginning, we have discussed the de Broglie concept of matter waves. Then we have discussed the importance of wave function, Schrodinger time independent wave equation, Schrodinger time dependent wave equation, and significance of psi and its properties, and finally the application of Schrodinger time independent equation, which is particle in one dimension box. So this we have discussed in the chapter. So this chapter is completed within 10 minutes. Today I will give the introduction to EM theory. Only introduction I will be giving. I am not going to start any syllabus, but introduction is must for electromagnetic theory. Did vector calculus is started for you in mathematics, unit 5? Students respond.
Yes, sir.
So you have some idea what is divergence of a vector, curl of a vector, line integral, surface integral. Okay, Neeraj?
Surface integral explaining, sir, now.
Volume integral is not, but the basics you know. Okay.
Yes,
So
sir.
then
Line
it is
integral completed, sir.
okay. So then it will be convenient for me also. Only I'll give 5 to 10 minutes. I'll give the introduction. I'll stop. And tomorrow in my regular class, I'll start actually the EMT, Maxwell's equations, which are very important. The last chapter in my syllabus. So I'll start. I'll present the basics of electromagnetic theory. 1 minute, please. Is this visible, students? Take the heading electromagnetic theory. So where you apply electromagnetic waves, students? What you know about the electromagnetic wave? Somebody respond. Don't know? Girls? Yes. You're there in the
Sir,
class?
signals, sir.
Electromagnetic wave signals. Okay. Where you apply? What is an electromagnetic wave? Basically, it is there in the PPT also. The first slide it is there. Okay, electromagnetic waves, it's a combination of coupling of both electric and magnetic fields. They are transverse in nature. The electromagnetic waves are transverse. If the direction of vibration of particles of the medium is perpendicular to the wave motion, then it is called as a transverse wave. They are transverse in nature by varying the combination of electric field and magnetic field are coupled here. They travel in space and generally how they are generated, accelerated charges are responsible to produce electromagnetic waves. Even light is electromagnetic in nature, that also you know, because they travel at a speed of 3 into 10 power 8 meter per second. They have constant velocity in vacuum and it is nearly equal to 3 to 10 power 8. The light rays which are coming from sun, they are electromagnetic because they have to travel lakhs of kilometers through space. They are electromagnetic in nature. The velocity is 3 to 10 power 8 meter per second and the speed of light in terms of these electromagnetic waves it can be written as 1 by under root mu naught epsilon naught, where mu naught is permeability of free space, epsilon naught is permittivity of free space. And the electromagnetic waves they does not require any material medium to travel. So with that they can travel in space and any material medium they can travel. Even in space they possess constant velocity which is of the order of 3 to 10 power 8 meter per second. So in this chapter we are going to discuss what actually the basic field is because this is for energy production. Because many types of signals as you rightly said they are in the form of electromagnetic waves. So what are the fundamental aspects of electromagnetic wave? So there are certain basic laws given by Maxwell based on the basic concepts of electricity and magnetism. So those we are going to discuss in this chapter, Maxwell's equations. Then we discuss the concept of displacement current, which is new. It's not the ordinary conduction current. In space, empty space in dielectric medium, some current is there, which is not the current because of the motion of electrons or something. So it is called as displacement current. Charge because of charges, induced charges, we will be getting some current. So we are discussing that displacement current also. Then plane electromagnetic wave equation we are going to discuss. And finally, the Poynting vector, which describes the energy, how energy can be transferred from space to a given device. So it is based on that Poynting theorem, transfer of energy. That also we are going to discuss in this chapter. But in the today's session, only the fundamental basics which are required to understand electromagnetic field we will be discussing. So the inherent characteristic of an electromagnetic wave is its frequency. So the frequency is unlimited from 10 to the power of 4 hertz to 10 to the power of 20 hertz. Electromagnetic waves are having a so the frequency remains unchanged, but its wavelength changes when the wave travels from one medium to another medium. So this is the beauty of electromagnetic wave. The frequency will not be changing, but the wavelength will be changing. A little bit fuzzy, you can say, and they follow the principle of superposition. And light vector, that is light is also electromagnetic in nature, is the reason for the optical effect due to electromagnetic wave. Here you see the electromagnetic wave, a magnetic field and an electric field is coupled here, so it travels in this direction. The distance between two successive Tresor troughs is equal to the wavelength. So this is the representation of an electromagnetic wave. And also you have a Fleming's thumb rule also. So how the electric field and the magnetic field and the motion of a particle will be there, it can be used, explained by using this one. So the electric field is indicated with an arrow and the magnetic field is in the circular form. So in this way, the electric field and the magnetic field and the motion of the wave simultaneously will occur in space or in a given medium. So this how an electromagnetic wave can be transmitted, how the electric field is converting into magnetic field and magnetic field into electric field by some equations. Maxwell gave some mathematical equations that we are going to discuss in this chapter. So why you have to study these electromagnetic waves? Because there are numerous applications. All these radar system, aeroplane, space rockets, all they take these electromagnetic signals only. Basing on that, they can travel. Because relatively they should move in the Earth's atmosphere. For that, they need a prompt signal that is nothing but an electromagnetic wave. And also in medical and dental inspection, medical diagnostics, and all your microwave and domestic kitchen application and appliance, it is based on electromagnetic radiation, electromagnetic waves only, and also your television, radio, older one, telephone, all they work on the principle of the propagation of electromagnetic wave. And also in communication, all these two mobiles are connected. How many mobiles you are connecting? Because energy spectrum is now, it's a property of intellectual property of a country. That's why 2G, 4G, 3G, everything, it has a lot of demand. And all our mobile networks, they are based on the propagation of electromagnetic signals only, even in satellite communication. So these are applications of electromagnetic waves. So electromagnetic wave, it is a coupled time varying and electric and magnetic fields that propagates in space. So actually this is the basic definition of an electromagnetic wave. So you know the orange color one, it is an electric field, and violet, it is a magnetic field. So both electric and magnetic fields, they are coupled and they vary with time. Coupled electric and magnetic fields which are varying with time that propagates in space can be taken as called as an electromagnetic wave. So this is, as I said, all these are applications of these electromagnetic waves, starting from the frequency range 10 to the power of 4 hertz to 10 to the power of 20 hertz. Optical frequencies, the 10 to the power of 15, which are photon zones. Then molecule frequencies 10 to the power of 16 hertz. Then atoms at 10 to the power of some 18 or something. Atomic nuclei 10 to the power of 22. They may vary. So all the emitted or absorbed radiation is electromagnetic. So for different applications, for AC power, for CRT monitors, different frequencies are required for mobile, for cells and microwave and satellites and the sunlight. You can see the energy spectrum of the electromagnetic wave for gamma rays, X-rays. So from 0 to infinity, you can say. So the frequencies are same and the wavelength will be changing as the device medium is changing. So these are the applications of electromagnetic waves. And some small basic definitions you should know. The first one is divergence of a vector field, because all this we are going to apply in Maxwell's equations. So you know operator del, which is a spatial operator. So the scalar product of operator del with vector A is called as divergence. Okay. So the divergence of a vector at any point can be defined as the amount of flux diverging from that point. So this is divergence. So it is a scalar product. So operator del is represented by I into dou by dou x plus j into dou by dou y plus k into dou by dou z. Let us define a vector A. It is IAX plus JAY plus KAZ. Remember, even though the bar is not there, you can assume vector it is vector. So it is understood. So the divergence of A can be written as div A, which is equal to del dot A, that is scalar product. So I into I dot I is equal to j dot k, that is k dot k, which is 1. So finally you will be getting del dot A is equal to dou AX by dou x plus dou AY by dou y plus dou AZ by dou z. So this is the divergence of a vector field. Suppose in physical sense, if the vector A represents the velocity of a fluid at a point, then if you calculate the divergence, then the divergence of A will give you the rate of flow of fluid at that point. So you know the velocity of the fluid, you use this operator so that you calculate the divergence, then it straight away gives the rate of flow of fluid, how much fluid is flowing per unit time from that point can be given by the divergence of that vector. So this is for any mathematical fluid mechanics, you need this divergence, and div A or del dot A is equal to 0 means the net flux diverging from that point is 0. That is how much fluid is coming from that point, the same is leaving from that point. So net flux is equal to 0. It is represented mathematically by del dot A is equal to 0. So this is the divergence of a vector field. The scalar product of operator del with a vector is called as divergence. Del is a spatial operator which is I into dou by dou x plus j into dou by dou y plus k into dou by dou z. Let us define a vector A. Then del dot k is a div A which is dou ax by dou x plus dou ay by dou y plus dou az by dou z, because I dot I is equal to j dot j is equal to k dot k, which is 1. It is a scalar product. So if a vector represents the velocity of the fluid, then the divergence of that vector will give you the rate of flow of fluid. Divergence of A 0 means the net flux diverging from that point is 0. This is the divergence of a vector field. And second one is curl of a vector. So the vector product of operator del with the vector f is known as curl. So previously it is a scalar product, now it is vector product. So the vector product of operator del with the vector f is known as curl. So let del is I into dou by dou x plus j into dou by dou y plus k into dou by dou z, and define a vector f as I f x plus j f I plus k f z. Then curl f is del cross f, which is in a matrix form. You know all this. Ijk, then dou by dou x, dou by dou y, dou by dou z, fx, fy, az. So if you want to calculate, it is I into dou fz by dou y minus dou fy by dou z, like that. You can write these components. So what actually the curl represents? The curl of a vector f at any point gives not only the magnitude but also the axis of rotation of the vector at that point. It not only gives the magnitude but also the axis of rotation of the vector at that point. So if you find the curl, it not only gives the magnitude but also the axis of rotation of that vector also. It is directional. It gives not only the magnitude but also the direction, axis of rotation. So the vector product of operator del with the vector is known as curl of the vector. Then line integral. So all this I think you have there in the mathematics. So the integration of a vector along a curve is called as line integral. You take a closed curve, you integrate this. So the integration of a vector along a closed curve is called as line integral. You can see the diagram in the three-dimensional space. It's only a one-dimensional concept. So A is a vector and dl is a small element of length along a curve. Then the line integral is represented by line integral A dot dl, or single integral A dot dl also you can write. So what is the physical significance? If capital E represents the electric field intensity at a point, then the line integral of E gives the electrical potential at that point. So you know E is the electric field intensity. If you calculate the line integral of that one, it gives the electric potential or the potential difference at that point. So by using this operator, integral A dot dl, you can calculate the potential at that point. You extend to two dimension, it will be a surface integral. So the integration of a vector over a closed surface is called its surface integral. In previous case, it is along a curve. Now it is over a surface. So if A is a vector and ds is the small element of area, then the surface integral is represented by that symbol A dot ds or double integration A dot ds. So line integral is one-dimensional concept and the surface integral is a two-dimensional concept. So surface integral A dot ds, it is where A is the vector and ds is the infinite element of area ds. If you extend further, it will be volume integral. So the integration of a vector along a closed volume is called its volume integral. So if A is a vector and dv is an element of, it's not length, it's a volume, then this volume integral is represented by triple integration A dot p, or with that symbol A dot b, you can say. So this is line integral, surface integral, volume integral. And there are three theorems are there: Gauss divergence theorem, Stokes theorem, and Green's theorem. As per our syllabus is concerned, we require only these two: Gauss divergence theorem and Stokes theorem. You must remember this statement and the mathematical expression. So what actually Gauss divergence theorem in mathematics you will be doing in detail, but only here you should remember the concept and the theorem. The surface integral of a vector A taken over a closed surface S is equals to the volume integral of divergence of A taken over a volume enclosed by the surface. So here if you see the expression, in the left side you have surface integral, which is two-dimensional concept, and in the right side you have volume integral, which is 3-dimensional. So a 2-dimensional quantity is expressed in 3-dimensional quantity by an operator divergence. So the same vector, it is with divergence, it is representing the surface integral. So a conversion of a 2-dimensional quantity into 3-dimensional and vice versa by some apparatus. So this is Gauss divergence theorem. According to this theorem, you should listen this carefully. The surface integral. So it is a second 2-dimensional concept. The surface integral of the vector A. So surface integral, double integration A over a closed surface. That's why we took DSS, double integration A dot ds. This is equals to the volume integral. Volume integral is triple integration of divergence. That's why we took del dot K. So divergence del dot K over a volume enclosed by the surface. So this is called as Gauss divergence theorem, and sorry, it is not ds, it is dv. I will correct this one. Del dot by dv. This is Gauss divergence theorem. Similarly, Stokes theorem. Stokes theorem is it explains a quantity in 1 dimension to 2 dimension. So the line integral of the vector A taken over a closed curve L is equals to the surface integral of a curve and surface integral of curl of A over a surface is enclosed by the curve. So here the line integral of a vector, it is a 1-dimensional quantity. It can be equated to a 2-dimensional quantity by taking the curve. So the line integral of a vector A taken over a closed surface is equals to the surface integral of curl of A over the surface enclosed by the curve. So these two theorems we should remember for the derivation of Maxwell's equations. Actually, up to this is not in the syllabus, but you should know all these before going to this Maxwell's expression, Maxwell's equation. So in tomorrow's class, I'll take Maxwell's equations, some electric, what is electric flux, what is magnetic flux, some basics are there. Along with that, I'll start Maxwell's equations. 4 important derivations are there. So you should write those derivations while I am giving in PPT, because they will be coming in the exam, definitely Maxwell's equations. Tomorrow again, I will repeat this in brief, and I'll explain what is electric flux and magnetic flux. Then straight away we'll start Maxwell's equations. I think time is up. I have to stop now. So I'll give attendance to all of you. Okay, because maximum strength is there. I'll give attendance. Okay. Any doubts in this? Next, which class we have, students?
BEE.
Okay, I'll stop here. Thank you. I'll give attendance to all. So when you are coming, how to write the record? I think all you know. The writing part should be on the right side. The diagrams, tables, figures, etc. in the left side. And in the manual, when the graph is corrected, that you carry it and you can keep in the experiment. And those who have done this FEG and pay injection, you have to complete the write-up part, because you didn't show the result. Thursday, when you are coming, you get it corrected, then you submit the record. That you should do. And assignment, you should write in the assignment book only, and you have to submit physically when you are coming for the next lab. That means next Monday. And exam notification has been given. It is shared in your WhatsApp group, and go through it, and within time you have to pay the examination fee. Don't delay this, and all this you keep in mind. And tomorrow, first hour, I will take this Maxwell's equations. Thank you.